welcome to page 2. And now what we're going to do is we're going to graph a direction field, a slope field, based off of given an autonomous first order differential equation. And so when we're going to do these by hand, they're actually not going to be that difficult because our differential equations are all pretty much depending on y. Then what's going to happen is I don't have to worry about drawing a bunch of x, y's, a bunch of dots on our coordinate plane, because it's as we go from left to right, x is not playing a role into what the differential equations look like because it's all dependent upon y. So just as we go from left to right on the horizontal line, it's going to pretty much be the same. As we go up, it's going to vary. And so the first thing that we want to do is we want to consider this first order autonomous differential equation. All right, and autonomous, noticing that there are none of our independent variables are in our solution for our differential equation. And the initial condition y of 0 is equal to y sub 0. So by hand sketch the graph of a typical solution, y of x is equal to the initial condition has the given values. So if we're told that we're starting at y sub 0 is greater than 1, what's our graph going to do? For B, but if we're starting from between 0 and 1, for C if we're starting between negative 1 and 0, and for D if we're starting between if we're starting below negative 1. All right, so the first thing that we want to do is kind of go up here, and we want to find our critical points, because our critical points is where our graph for the differential equation is going to tend. So let's go ahead and we're going to take our equation and we're going to find all the critical points. Well, finding the critical points of a differential equation is where you set the differential equation equal to 0. So we're going to do that. So 0 is equal to y squared minus y to the 4th. Now let's go ahead and pull out a y squared. We do that, we're going to get pull out the y squared, we get y1 minus y squared. And then again we can factor that, and we're going to get y squared, and then 1 plus y, 1 minus y. And our zeros are going to be y is equal to 0, negative 1, and positive 1. All right, so these are our critical points. And so what we want to do is we want to find out, well, what's going on between all of our critical points. And so, I don't know if you remember, making these little charts back in, calculus. I mean, you've made these probably in Algebra 2 and Algebra 1. Depending on where the graph is going to go, maximum, is your graph rising, is your graph lowering. So we're just going to go ahead and make a graph. We're going to go from negative infinity to positive infinity. We're going to put our critical points there, negative 1, 0. When this tells us where our graph is tending to, is it tending, to 0? Is it tending towards negative 1? And what we're going to do, and I hate that it's done before attractors, repellers, but I'm just going to go ahead and show you what the graph's going to look like. So we're going to plug in a number, a constant, in between negative infinity and negative 2. So we can just pick any value. We're going to pick negative, pick negative 4. You pick negative 2, negative 3. I just picked negative 4 just because it's bigger and it's easier to tell just by looking. So if I put in negative 4 into our differential equation, but in factored form, negative 4 squared is going to be positive. And that one we can kind of eliminate because it's always going to be positive. All right, so we plug in negative 4 here. 1 plus negative 4 is negative, and then 1 minus negative 4, well, that's positive. So then we're going to, because that's positive, we're going to be going up. All right, from negative 1 to 0, let's go ahead and take negative 0.5, plug it in. Always going to be positive for y squared. 1 plus negative 0.5, well, that's going to be positive 1. I'm so sorry. When I was looking at that, should be negative, because if this is positive, that's negative, then that first value should be negative. So that should be going down. All right, from negative 1 to 0, we get negative 0.5. Plug it in. That's going to be positive. That's going to be positive. Plug into 1 minus 0. So that's going to be positive. And so we're going to be going up. 0 to 1, positive, positive, positive. For all those, we can just pick 0.5. And then if we pick 2, we're going to be positive, positive. But then for that last one, we're going to be negative. So we'll be going down. All right. And so it's best to see it because this isn't, we drew it horizontally because that's what we're used to seeing, but really, because these are y's, we can draw this vertically. And we can say negative infinity to positive infinity, negative 1, 0, and 1. And this tells us what our slope fields are doing. And so from negative infinity to negative 1, it's going down. So all of our slope fields are going to be pointing down. From 1 to 0, from negative 1 to 0, all of them are going to be pointing upwards. And so the same thing for 0 to 1. They're going to be pointing upwards. And again, these are for our y's. And then the last one, which is 2, is going to be going down. So from left to right, the x's aren't going to play any role except for allowing us to know as we go through time. All right, but the y's, they're telling us, is the slope fields, pointing up or the slope fields pointing downwards. And so now we can go ahead and fill this out. So for A. All right, if we're going to, by hand sketch the graph of a typical solution y of x when we're given a value that's greater than 1, then what's going to happen is, let's go ahead and just do that in black. There's x. So here's the x-axis, there's the y-axis. We have a critical point at 1, and so let's go ahead and make that point there. That's not straight. I'm so sorry. Skip this if y'all want to. No, I'm done. I'm done. That should be straight. So if that's at 1, and we're starting above 1, we know that since 1 is a solution to the differential equation, it's going to be constant at 1. So if we're starting above 1, then our graph is just going to start above there, and then it's going to tend towards 1. If we do B, and now we're between 0 and 1, so let's go ahead and draw another graph. So there's x, there's y. And now, again, we have solutions at 0, so I'm going to go ahead and, get my solution at 0. And then I'm going to do my solution at 1. Then what it tells me is that I'm going from 0, go ahead and highlight this, from 0 to 1, the graph is going to tend towards 1. So then we're starting, if we're between 0 and 1, then we'd start closer to 0, and then we'll end up at 1. So it looks something like this. All right, let's do C. It's going to be very similar, but now there's x, this is y, and I'm going to do, so this is 0, this is negative 1, and so our graph here, notice we're tending towards 0 between negative 1 and 0. So again, we're going to start close to negative 1, and then we'll be finishing up at 0. And then for the last one, D, there's x, there's y. And go ahead and, this is negative 1. And our graph is going to be tending. So it's going down. So we're starting close to -1, and then we're going down to negative infinity. So it looks something like that. All right, attractors, repellers. If y of x is a non-constant solution of the autonomous differential equation and c is a critical point of the differential equation, there are 3 types. Of behaviors that y of x can exhibit near c. All right, the first is going to be, it could be an attractor where, you know, both the graphs are going to be tending towards that constant. And so it's going to be, you know, what we had for 1, where they both tended towards 1 for that previous example. That's an attractor where we're going to, you know, that same critical point. Could be a repeller, it's bouncing off of that critical point. So like what we had for -1 up here, we could tell that, oh, it's going, you know, away from -1 in both spots. So that's going to be a repeller. And then a semi-stable one is where your critical point is in between a pathway. They're either both going up or they're both going down. The first order differential equation is autonomous, and the slopes of linear elements along any horizontal line must be the same. Again, why? It's because our differential equation is all in terms of y and not of x. Since x is the horizontal axis, as we go along the horizontal axis, you know, your y values aren't changing at all. I'm sorry, well, as you go along, none of your values are going to be the same. I'll give you like a brief example. So an example of if we graphed a autonomous differential equation for, you know, into the slope field, you know, as we go from left to right, they're all going to be the same. And so this would be in a way where if you went, you know, in a vertical direction, you know, they're going to change, but as you go horizontally, they're not going to change. They're all going to stay the same. And again, the reason why is because we have a differential equation that's all in terms of y and not in terms of x. And so that's why as you go along a horizontal line for your slope field for an autonomous differential equation, it's not going to be changing along that horizontal line.